commission new instruments and so on.
So can you...
I wanted to tell you about the observatory first.
Yeah.
We're sitting here in the control room of the 4.2 meter Wiliam Herschel telescope, and this is one of 3 telescopes here run by the Isaac Newton group. The others are the 2.5 meter Isaac Newton telescope and the 1 meter Jacobus Captain telescope. And this is a UK Dutch-Spanish collaboration, so most of our visiting astronomers are from these 3 countries. Although actually anybody from anywhere in the world can apply to get time on these telescopes. The telescope's been here for quite a while now. It's been observing for 20 years. It's a classical Cassegrain telescope. So we'll see a picture in a minute. There are... One of the advantages of this telescope is that it has many focal stations. You can see on the left and the right the 2 Naismith foci, and there are in addition 6 other foci of the Cassegrain focus, several folded Cassegrain foci, and a prime focus. And this means that we can put cameras at any of these foci. It gives us a great deal of flexibility. So, for example, tonight we have something like 5 cameras active, and it means that astronomers during the night can switch between any of these cameras. So, for example, if the supernova goes off, then we're all ready to take an image of that supernova with one of these cameras. And this flexibility is also a strength for astronomers who want to bring their own cameras on, visiting instruments, because we can mount these at the Naismith foci and switch to these cameras whenever they want to, or switch back to the other instruments, depending on the conditions during the night.
So quite a versatile telescope. I'm being told that you have students as guests tonight?
Yes, we'll come to those a little bit later in this segment.
Okay. So tell me, what are you doing tonight?
Tonight is actually a test night. We're testing the laser guide star for the adaptive optics system. This is another special feature of this telescope. The adaptive optics, the aim of the adaptive optics is to take out the blurring caused by the atmosphere, what we call the seeing. And although to the naked eye, this is not visible, and when you look with a telescope at the stars, it's a little bit like looking through the surface of a swimming pool at the surface of the pool, and you see some blurring of the bottom of the pool, and it's the same when a telescope looks at the stars.
And so you mentioned the laser guide star. Does it mean that you shoot a laser in the sky?
Well, so the aim of you can see here the core of the adaptive optics system on the Wiliam Herschel telescope, and this is a deformable mirror. This consists of 76 segments, and this is in the path of the light going from the star to the science camera. And if you imagine a column of light coming from the star down onto the primary mirror of the telescope, we shrink this column of light and image it onto this mirror. And then each of these 76 segments in this deformable mirror can be moved in with 3 degrees of freedom. It can move in and out, and it can tip and it can tilt. And by adjusting these very fast, up to around 100 times a second, then we can take out most of this twinkling in the atmosphere, the seeing, which degrades, which blurs the image. And we've got a nice example here. This is actually taken with using our laser guide star adaptive optics system. It's an image of Uranus on the left-hand side. You see Uranus with the adaptive optics on. And on the right-hand side, it's a picture with the adaptive optics on. And you see the spectacular difference there. On the right-hand side, you can see the cloud bands in the atmosphere of Uranus. And you can also see the moon around. So
what for do you need the laser then?
Okay, so the tricky bit of adaptive optics is that you need a bright star near the object you're looking at. So, and only around 1% of the objects in the sky have a star close enough to do that. So what astronomers have done, at several observatories around the world, is to create artificial stars. And the function of the laser is to create an artificial star.
So that's a rather neat trick to correct for the blurring of the atmosphere. So you're testing this system tonight?
So tonight we're testing the laser guide star, and Yuri will tell you a little bit about the tests that we're doing tonight.
Okay, so the laser is launched to distance of 15 kilometers. Essentially, it is focused at this distance of 15 kilometers from the telescope. At the exit from the beam launch telescope, it has diameter The beam has the diameter of 35 centimeters, and the focus is about 8 centimeters. And we are observing this with our adaptive optic system and correcting the wavefront in accordance to the movement detected or changes of the wavefront detected by the wavefront sensor. And tonight we are doing some technical tests. We want to evaluate what is the dependence of the telescope response of the response of the entire adaptive optic system as a function of elevation. Because in our case this changes. If the telescope is at a lower elevation, the laser beam goes through different layers of the atmosphere and through more atmosphere. So we have to evaluate this to be ready for scientific observations.
Okay, so let's come to the students. You have students around in a night where you're doing technical tests. What are the students doing here?
Well, the students are actually not observing here. They've been outside.
Oh, they're working outside. In the cold. You keeping them fresh?
Yeah, well, I'd like to introduce now Charlie Bartley from Marlborough College in the UK.
Hey.
And Damien Cookhouse, who's one of the students. And they've been here tonight. Standing outside in the cold. I've been looking at the sky.
Hi guys.
Thank you, Chris. Hi, good evening. We're incredibly lucky to be here with the ING group, and it's amazing for the students and us to have observing in this site. We've joined some observers in the Isaac Newton telescope for the evening, and also the ING have arranged for us to join the UK Moonwatch Week, which has been organised by the Society for Popular Astronomy, and we've been observing in the Jacobus Captain dome right at the top of the mountain. And Hamish, what have you found the most exciting?
Well, I think one of the really exciting things it's the location, because it's beautiful and it's just perfect for astronomy. For example, these observations we do at the Jacobus Captain have been infinitesimally better than anything we've done here in the UK, because it's just such a good location. But really, one of the exciting things I've seen is the firing of the 10-watt laser here from here at the WHT, which is really spectacular, and I thought that was tremendously exciting.
Exciting. I mean, so I guess the night has been quite clear then.
It's been good, very good.
And did you have a chance to see the laser from outside?
We saw it as we walked down.
We came down from the Jacobus Captain to do this, and the laser was being fired outside. So yeah, we got a chance.
Okay, so how much longer will you be staying?
We're going to stay one more night. I think by the time the students and myself have been up all tonight and all tomorrow night, it'll be good opportunities to go down. But it's very amazing to be here in this location with the dark skies, and
Very lucky.
for the students to see the researchers working firsthand.
Excellent, first-hand experience. So I wish you a good night, some more exciting observations, and great experience, and I hope that you all become astronomers. Good. And so what will the Wiliam Herschel telescope be doing for the rest of the night? Finish the technical test, I guess. Or some of the students in the back. Hi guys.
Yeah, we've got some other students coming.
Do we have time to show you a movie?
Absolutely.
Yep.
Yep. Do that quickly.
So we'd just like to show you something that's connected with our science highlight of the month, which is something that's appeared in Nature last week. And it's a story about an asteroid which was seen approaching the Earth. And this happened in last October. And it was predicted to impact the Earth. And in fact, as you can see here, it collided with the Earth. It impacted the atmosphere about 37 kilometers above northern Sudan and exploded and left a few fragments on the ground. But during its journey towards the Earth, astronomers were able to take a spectrum of it. And this is the very first time the spectrum has been taken of an asteroid approaching the Earth and then to impact with it. And this spectrum was taken by the WHT. So this is another first for the WHT. It's the first ever spectrum taken on an asteroid.
That's excellent.
A And this means that the astronomers who found fragments of this asteroid can relate the rock types of these fragments to the spectrum of the asteroid they see.
I'm being told that we have to move on now, but that was a very nice final touch. So thank you very much for joining us, and have a good night then.
Thank you very much.
Bye-bye.
Bye.
You're watching Around the World in 80 Telescopes. Stay with us for another telescope on La Palma.